Okay, so I think we can get started. There are a few more people who are going to continue joining in over the next few minutes. Um, am I audible?
Yeah, you're audible.
Okay. So good evening, everyone. There are, I think, about 50 of you here. So this talk is kind of basically on the Zoom call people from within our community today. There's also a live stream link that maybe one of us can put up on the chat box. So once again, good evening, and we've been kind of waiting for this talk for over a week now. As you all know, we have the summer solstice project series that are going on in Naxxatra, and out of the two basic divisions, one of the categories involves the study of astroparticle physics with a special interest in neutrinos this time. And as you might know, the second category is more towards observational astrophysics and the study of electromagnetic radiation. Um, so as we go ahead in learning astroparticle physics, we felt it was very necessary for people to get a one strong understanding of what particle physics is all about. So we were very, very lucky to have Shalini with us today. So I'm just going to go ahead and give you guys a little bit of her background. So Shalini has completed a bachelor's and master's degree, a BS/MS dual degree from ISER, Kolkata, and she was under the Inspire Fellowship from the Government of India with a master's thesis titled An Alternative Algorithm for Charged Particle Trajectory Reconstruction at the CMS Detector. So her area of specialization is particle physics. She has held multiple internship positions in both phenomenological and experimental particle physics during her studies. These projects explored ideas from neutrino oscillations and neutralino dark matter in 2017, MC validation of an RTV to search with the Atlas collaboration in 2018 from the University of Glasgow, and studies on the fake tau background with, again, the Atlas detector from Charles University. She has also participated in the outreach activities of CERN at the Colors of Ostrava in 2019, Czech Republic. Currently, she's a PhD student with the Atlas collaboration at IFAE Barcelona, working on searches for new physics in multi-lepton final states. So she is currently at CERN, so I think all of you might have a whole bunch of questions for her. What we'll do is we will first listen to her presentation. She's going to be introducing us to some really important introductory topics today. And since a lot of you are new to particle physics, this is great. But also, I know that some of you have a lot of strong background already. So please use this as a platform to ask the right questions, and we will have 15 minutes dedicated to that. So once again, welcome Shalini to Naxxatra's platform. Very excited to have you here, and let's get the evening started.
Thank you so much, Sitara. I'm quite excited to be here. I'm glad you guys invited me to talk about particle physics and my work in general. So today the plan is to have sort of a bird's eye view of what is particle physics. We'll talk about the standard model of particle physics. We're not going to go into too many details, but in a nutshell, we'll talk about particle accelerators and how do you detect particles. Let's dive right in. So we have the standard model of particle physics, which aims to explain how nature works at its most fundamental level. So the idea in a nutshell is quite simple. All known matter is made up of a few building blocks, a few fundamental building blocks, and the interactions between these are to be governed by four fundamental forces. So the standard model tells you that there are two kinds of particles. You have fermions, which make up all the matter around us, and then you have bosons, which are the force carriers. So the fermions exchange bosons to interact with each other. Fermions, what distinguishes fermions from bosons is their spin. Fermions have what is called a half integer spin, and bosons have integer spin. Now, let's take a quick digression to understand what I mean by spin. So in particle physics, we have discrete numbers that can be used to identify the type of a particle and to describe how it interacts with other particles via the fundamental forces. So these are like the identity card. They are a part of the identity of the particle. So they are called internal quantum numbers. And spin is one such intrinsic quantum number. For example, if you have the ID card of a proton, you would say that, yeah, my name is the proton, my spin is half, my charge is +1, and these spin and charge is something that will not change. A proton is always going to have spin half, charge +1. Now back to the standard model. So this formulation of the standard model was finalized somewhere in the 1970s. And it has been continuously tested ever since, and it is the most accurate theory of matter that we have till date. On this slide here, I have the ingredients that are the particles that are involved in the standard model. So the two kinds of particles, you have the fermions on the left, which are of two kinds, the leptons, and then they're the quarks. And then you have the bosons, which are, to remind you, the force carriers, which help the fermions to interact with each other. Now, the standard model of particle physics is a theory of 3 out of 4 fundamental forces that we have in nature. It does not have an explanation for gravity, which is why I have a big, large cross on top of gravity. We will talk about this later on in the presentation. Let's start with the fermions. Fermions are of two kinds. You have leptons and you have quarks. The most familiar guy that you see over here is the electron. So this is what you see in the atom. You have phenomena like, electricity, lightning, all because of the electron. It has a charge of -1. And then you come to the heavier cousin of the electron, which is called the muon. So muon basically is like a really heavy electron. And an even heavier electron would be called the tau. So the leptons are arranged in 3 generations. The first generation is the electron, which is stable, and you would see phenomena happen around you because of the electron. Muons are the next stable particles, the second generation, and then come the tau, which is not stable. And so in each generation, you have sort of a corresponding neutrino, which is expected to be of the same flavor. Now, flavor is yet another quantum number. So in some interactions where the electron is produced, you would have a neutrino also produced with it of the flavor electron type. So you will have an electron and an electron neutrino being produced together. So these 6 particles together are the leptons that are the standard model of particle physics. And then you have the quarks. There are again 6 of them, and we are not very creative in naming them. You have up, down, strange, charm, bottom, and top. So the familiar ones over here will be the up and down quarks because they make up protons and neutrons. So over here I have the proton, you have 2 up quarks and 1 down quark, and a neutron, which has 1 up and 2 down quarks. Now, quarks have yet another quantum number called color. And there are 3 kinds of colors that a quark can have. It can be red, blue, or green. Quarks are never found lying around in nature. They cannot just hang around. They always have to form a bound state, which is color neutral. So these 3 quarks which hang around together would need to be of red, blue, and green. So they will form sort of white in a way. Now, moving on to the bosons, you have the 3 forces that are explained by the standard model of particle physics. The first one is the strong force, whose carrier is called the gluon, and there are 8 of them. Gluons are the guys which hold these quarks together to form bound states. So in the proton and the neutron, these little wriggly lines here are representing gluons, which are holding it together. In fact, the strong force is called the strong force because it is the strongest of all the other 3 forces. It is responsible for holding together nuclei. So inside the nucleus, you will know that you have protons, you have neutrons. Protons are positively charged, neutrons have no charge at all. And 2 protons hanging together in a bound stable state of a nucleus is not actually possible because of electromagnetism. Like charges repel, so 2 protons should actually fly apart together. But it is because of the strong force that they are held together to form this nucleus. Next, we come on to electromagnetism, and this is the one that we are all super familiar with because the force carrier for electromagnetism is called a photon, And this is basically a particle of light. It helps us see the world around us. And finally, the third guy is the weak force. There are three carriers for the weak force. You have two W bosons, a W plus, a W minus, and then you have the Z boson. The weak force, an example of what it does is it is responsible for the energy generation in the sun. So in the sun, what happens is a neutron gets converted into a proton, and in the process throws out a W boson, which further gets converted into an electron and a neutrino pair. So that was your standard model of particle physics, but we are still missing out one really important guy, the grandfather of them all, the Higgs boson. So according to this theory, right after the Big Bang, all elementary particles that were produced were massless. So from our observations, we know that the electron has a mass. So what theorists needed to do is add another ingredient into the model that would make the particles massive. In 1960s, three scientists, Braut, Englert, I hope I'm pronouncing these right, and Higgs, laid down a proposal for a field called the Higgs field. And the idea was that the Higgs field will get switched on in a way right after the Big Bang. Interactions with the Higgs field is what will give mass to particles. So the stronger you interact with the Higgs field, the heavier you're going to be. So let's look at this chart over here. You have the top quark, which has the strongest interaction, in technical terms, coupling to the Higgs field. So it is the most massive particle that we know. And particles which do not interact with the Higgs field, like the photon and the gluon, are the ones that are left massless. So how do you know about the existence of the Higgs field? How do you see, in a way, the Higgs field? So the idea is to excite this field. So the quantum excitations of this field is going to produce the quantum of this field, which is called the Higgs boson. It was another particle. But this Higgs boson is unstable and it decays almost immediately. It can eventually give us particles like electrons or other bound states of quarks that we know and we measure. And we have to, after that, work our way backwards to realize, hey, okay, this came from the Higgs boson. And I have a small exercise for you over here. Later on in the slides, we'll again come back to this little topic. In a nutshell, again, whatever we have discussed so far is there on this slide. You have the first three columns, which are the fermions. You have quarks, 6 of them on the top. You have leptons, 6 of them on the bottom. Now, all of these particles have an antiparticle as well, which is basically the same particle, but with the same properties, except the charge of the particle and the magnetic moment of the particle is reversed. So corresponding to each quark, you will have an antiquark. Corresponding to every lepton, you will have an antilepton. And finally, you have your force carriers, the bosons. You have the gluon for the strong force, 8 of them. You have the photon for the electromagnetic force. And you have the 3 weak bosons, the Z, W plus and W minus, which carry the weak force. And finally is the guy which gives all of them mass except the photon and the gluon, and that is the Higgs boson. Now, a reality check. We have discussed about these interesting particles, interesting theories, but can you actually see these fundamental particles? And the answer is yes. In fact, one of the earliest particle detectors that we ever had was called a cloud chamber. And I have a small representation of a cloud chamber here on the left. The idea is to have a sealed container, a sealed environment of supersaturated vapor of alcohol. Usually ethyl alcohol is used. So on the top, you have a lid which seals the container and is usually maintained roughly at room temperature. And on the bottom, you have usually a metal plate, a metal conducting plate in contact with dry ice. So you create sort of a very cold environment on the bottom of the jar. And on the lid, usually you can have an alcohol wick, or you have something, a material like felt, which is drenched with ethyl alcohol. And this condition creates a supersaturated vapor of alcohol. And what happens next is pretty interesting. So when energetic charged particles pass through this chamber, they interact with the gas molecules and they ionize them. Now, around these ionized particles, condensation occurs, and this can be seen as a mist of, a trail of droplets right along in the chamber. And this lasts for a few seconds and this settles. In fact, you don't really need a radioactive source to actually see particles. You could see stuff like the cosmic ray background, for example. And here I have a small GIF. Let's hope this plays of, we're looking into, so from the lid, of what happens inside a cloud chamber. And this is not playing. Okay, sorry about that. And I have a link over here, which takes you to a DIY cloud chamber. They are quite simple to make, and it's a great idea to try it out sometime if you have a few hours at hand. Okay, one more thing that I included in my presentation today is a picture, a snapshot in time of what you expect to see inside a cloud chamber. And this is what it looks like usually. There are three kinds of particles that you can very usually see in this cloud chamber. The first one is the alpha particle. It is basically a bound state of two protons and two neutrons together. You can also see electrons and you can see muons. Now, as a small exercise, I would like you guys to take a minute or so to see if you can spot these over here. And here are a few hints. Alpha particles are heavy, so they would move very slowly through the mist. Muons are usually energetic, so they would zip past, and they're not as heavy, they're quite light compared to alpha particles. And electrons are not as energetic, so they would, wriggle about the place. So let's take a small moment over here. Look at this picture, see if you can find these three particles here. So the first one over here is an alpha particle track. So as I mentioned, they are heavy. They're bulky, so they would move more slowly, and lots of condensation would occur right across them, along them. So this over here is an alpha particle track. This over here is a muon track. Muons are energetic, so they would zip past the cloud chamber in a straight line. And finally, our electron tracks over here, it would curl up a little bit. It doesn't have as much energy to just zip past. And in many other cloud chambers, you can see electrons which actually spiral through. You can see an electron-positron pair being produced. It's quite exciting.
Ma'am, I have one doubt.
Uh-huh.
So if the particles are deflected, even that can be noticed, no?
Right. You can have a magnetic field around it. So you would have particles being deflected into opposite directions.
Thank you, ma'am.
No problem. Okay, so now that we have seen our first instance of a particle detector, why do we need particle accelerators at all? Where do they fit in the picture? Now, most of the particles that we have in the standard model are unstable. So they are going to be produced, even if they were produced, they would have decayed already. The visible universe right now is made up of mostly electrons, protons and neutrons, which basically form your atoms and molecules and us eventually. You have photons, which help you see stuff. And then you have neutrinos. Neutrinos don't really make up structures, but they are present all around and they hardly interact. They have very weak interactions. So to actually figure out whether there really exists, say, a Z boson or the Higgs boson, you would need to create it. And this is where the role of an accelerator comes in. An accelerator is a device that would propel these charged particles like electrons or protons to very high energies, close to the speed of light, and then collide them. So these accelerators can be of two types. You can have fixed target experiments in which you have a beam of particles and a stable target, and boom, there's a collision. Or you can have circular colliders in which you have two particle beams which are going in opposite directions, and finally they collide at a designated point. Now, what happens at the collision point is that energy gets spontaneously converted into mass. So E is equal to mc squared. This is where Einstein's famous equation comes in. At this collision point, you have conditions very similar to just after the Big Bang. And this energy can spontaneously transform into the mass, into different particles, exotic particles, some which we know, like, and we can study, like the top, like the Higgs boson. And you can also use this to search for new ones. And that brings up with another question: why do you need to search for new particles when you have such a successful theory? We will discuss this as well. The topic of particle accelerators will take us first to the largest scientific laboratory that we have in the world. So this was established, this is called CERN. It was established in 1940s with the vision to have a world-class nuclear research facility in Europe. This was just after the World War II. And now this is an example of coordination and collaboration for the whole world, really. So CERN is home to the largest and the most powerful particle accelerator that was ever built. So this is called the Large Hadron Collider, LHC. So the LHC was started up in 2008. It is 27 kilometers in circumference. It's a circular collider. It sits around 100 meters underground in a tunnel between, it's at the border between France and Switzerland. And it accelerates protons or heavy ions usually lead ions, to nearly the speed of light before colliding them at 4 main collision points across the ring. So there are 4 main collision points over here in the picture, and around each collision point, you have a specialized detector that is built. The 2 first ones that we go to are the Atlas and the CMS, which are basically general purpose detectors that we can use to study the standard model or to even search for new physics beyond the standard model. The LHCb is the Large Hadron Collider Beauty experiment, which specifically studies stuff like matter-antimatter asymmetry. They talk about studying final states in which there are B hadrons, that is, bound states of quarks which contain at least one B quark. And finally, you have the ALICE collaboration, which is basically a heavy, they usually study heavy ion collisions, which are lead nuclei. And at the collision point, what happens is a 5th state of matter called a quark-gluon plasma is produced. And in this state, you have finally the quarks and the gluons, which are free. So that's not allowed at the current conditions on Earth, but this was what happened a few seconds right after the Big Bang. So you have recreated those conditions and you can study how matter condensed, how things formed at all. Next, we come to particle acceleration at CERN. To produce these protons, to produce beams of protons, you need to produce protons. And the best place to start is a hydrogen atom. A hydrogen atom is a rather simple system. You have a proton and you have an electron that goes around it. The idea would be to ionize this. So you kick out the electron and then you're left with the proton. These protons are packed into bunches and then arranged into beams. Now, these beams are accelerated. So this is usually produced at the LINAC over here. And this is a linear collider where beams are accelerated using radio frequency cavities. And then they are shot into the next part of the acceleration system, which is called the booster. After this, they go into the PS, the proton synchrotron, following that to the SPS, the super proton synchrotron. After which, finally, so what happens is this acceleration is not a one-shot process. It takes place in multiple stages. And there are superconducting magnets which focus and bend the beam as it goes through its trajectory. Finally, the SPS, the beams in the SPS are shot into this really large ring, which is called the Large Hadron Collider. At the LHC, so finally you have 2 proton beams. The energy per proton beam is somewhere around 7 TeV right now, in the last time that the LHC was fired up. Let's understand what 7 TeV actually means. 1 electron volt is the amount of energy that is required to accelerate an electron through 1 volt of potential difference. And a TeV, or tera electron volt, is 1 followed with 12 zeros, electron volts. Now, if you have a flying mosquito around, the energy of motion of a flying mosquito is somewhere around 1 tera electron volt. But the LHC, what it does is squeezes this energy into a space which is a million times smaller than a mosquito. So this is where the magic happens. Now you have 2 proton beams that are circulating in this tunnel in opposite directions. Now these bunches pass through each of the 4 collision points that we talked about, the Atlas, CMS, LHCb, and the Alice. And these bunches pass each of these collision points around 30 million times per second. And per crossing, there are about 40 collisions. So you have 40 proton-proton collisions that happen. You can do a quick math to understand how many collisions that you're producing per second. Now, not all of these events that are produced are interesting. So we have something called triggers that would select something that may be of potential interest to physics, to new physics, or to the standard model. So these detectors are going to filter such events and retain only about 10 power 5 events per second. And then these are further processed before dumping into disks. So the rate is reduced to around 200 events per second. At the end of the day, from all the LHC experiments, we dump all the data into something called the data center, the CERN data center, which processes this data. It stores about more than 30 petabytes of data. So to get an idea of what a petabyte is, on Amazon, you have these 1 TB disks. And you take about 1024 of them, that would give you roughly 1 petabyte. Now you have produced collisions, and what happens next? You have particles that are produced, but now you need to detect them. To understand the basics of particle detection, let us go to the CMS detector. And most the other detectors as well have a similar strategy that they follow to detect particles. Around the collision point, the detectors are built cylindrically, more like an onion, you would say. The first part of the detector, which is closest to the interaction point, is called the tracker. It consists of multiple layers of silicon. And any charged particle that is produced at the interaction point, or any charged particle that is produced, is going to leave hits on the different layers of the silicon. It is more like a join the dots puzzle after that. So these dots can be used to reconstruct the trajectory of the particle that passed right through. Now, this entire system is immersed in a magnetic field of about 4 Tesla, which is, well, 10 to the power 5 times roughly, I would say, stronger than the magnetic field of the Earth. Now, these, because of the presence of this magnetic field, the particles as they pass, they do not follow a straight trajectory through the tracker, but they bend depending on the charge. And this bent curvature is going to help us understand the transverse momentum of the particle as well. After the tracker, you have something called the electromagnetic calorimeter, or the ECAL. And this is where the energy deposits from electrons and photons are recorded. After this, you have another calorimeter called the hadronic calorimeter, which records energies from charged and neutral hadrons. A quick reminder, charged hadrons, an example is a proton, and an example of a neutral hadron is a neutron. And finally, you have 4 additional tracking layers called the muon tracking system, and these are dedicated specifically to muon identification and detection. Now, in this whole setup, you cannot detect neutrinos. And energy momentum conservation dictates that the total amount of energy, which was zero before the event, in the transverse and in the longitudinal plane, has to be conserved after the event as well. So if you have any missing energy that you see, any sort of imbalance that you see after reconstructing all particles, you would assign this missing energy to neutrinos. So each detector at this point contributes to identifying a specific element. So say a trajectory in the case of the trackers, or an energy deposit in the case of the calorimeters. And these can finally be correlated to identify the particle. An example here is that of the electron. An electron is charged, so it would leave hits in the tracker, and it would deposit its energy ideally in the electromagnetic calorimeter. So if you see hits in a tracker which is correlated with an energy deposit right in the electrocalorimeter, you can guess that, yes, this was an electron that passed through. But if you see that there is an energy deposit in the calorimeter just hanging around, and you do not have a track that can be associated with it, you can guess that it possibly came from a photon, because photons do not have any charge. So let's do a small exercise over here. Suppose you observe that there are no hits in the tracker, but you have energy deposits in the hadronic calorimeter. What particle do you think it could be? Let's take a small moment over here and think about it. So you have no hits in the tracker, which tells you that it's not a charged particle, it's a neutral particle. But now you see, sorry?
Neutrino?
Well, it cannot be a neutrino because we cannot detect neutrinos with the current setup. Neutrinos will pass undetected and they would be reconstructed, I would say, as the total missing energy in the event. But as you see that there are energy deposits in the hadronic calorimeter, which means it's something to do with the hadron.
Is it neutron?
Yes, it'll be a neutral hadron. It can be a neutron. It'll usually be a neutral hadron, which leaves this. So you're right. Since an energy deposit in the HCal would mean that it's a hadronic particle, it has to be made up of quarks. That is one of the reasons why it cannot be a neutrino again. So you're right. This is a neutral hadron.
Excuse me.
Sorry?
Yeah, I'm audible.
Yeah. Tell me.
Yeah, ma'am. My question is, how will you come to know that this missing energy is due to neutrinos?
That is a very good question. So if you assume that all there is to the world is the standard model of particle physics, you would say that the only particle that I have not been able to detect is a neutrino. So the missing energy would come from a neutrino, because you again make the assumption that energy and momentum are conserved, and there are many more stringent tests that have been done to check this conservation law. But if there are particles beyond the standard model, there is a chance that this missing energy cannot be actually assigned to neutrinos. And there are analyses which deal with this in a very separate manner altogether. So yeah, thank you for your question. I hope this answers it.
Yeah, ma'am. Yeah, means there might be possibility that another charged particles or chargeless particle must be there.
Another particle which does not have any electromagnetic interactions or hadronic interactions might be there.
Okay, means related to dark matter or dark energy.
Yeah, that is one interesting idea, that yes, there are some theories, for example, a kind of supersymmetry theory, which tells you that there is a particle called a neutralino, which is again a good candidate for a dark matter particle. And these guys can actually maybe produced at the Large Hadron Collider and pass through undetected, and we haven't seen them yet. But
thank you.
Thank you for your question. That was a very good one. So now you know how to detect particles, and now comes the next part of things. Let's move on to see what you do after the particle is detected with the Atlas detector. Now, this is the detector that I work with. It is a general purpose detector, again, to test the standard model and to look for beyond standard model physics. BSM over here stands for beyond standard model physics. I have included another link over here where you can take a virtual tour of this detector. Now, for the purpose of understanding what happens after particle detection, let us take the example of the Higgs boson. Now, the Higgs boson was, well, 30 years after it was finally theorized did we actually find it. It was the final piece of the puzzle. It was announced by the CMS and the Atlas collaboration at CERN on 4th of July, 2021. And today what we're going to do is try to find the Higgs boson again. And if you remember from last time, today we're going to be looking at a Higgs boson decaying into two Z bosons. So you have a Higgs that is produced, you have two Z bosons, and they further decay into leptons. Now, this cryptic thing over here is what you call a Feynman diagram, and they can be used to represent the processes that take place in particle physics. You read them from left to right. So on the left over here, you have two gluons, which interact, produce a Higgs boson. This Higgs boson decays into two Z bosons. Each of these Z bosons decay into an electron and an anti-electron, or they can decay into a muon and an anti-muon, or, so you will have finally in your detector, you would see either 4 electrons, 4 muons, or 2 electrons, 2 muons. So this picture over here is actually a 4-lepton event where you have the first, this part over here is the Atlas tracker. You have 4 lines over here in blue and 2 in red, which actually represent the 4 leptons. You have these stars over here, which are actually the energy deposits in the electromagnetic calorimeter of the Atlas detector. The other layers are not represented over here. Now, this is not a very easy thing to do. This is like searching for a needle in a haystack, because this event, this sort of a picture may not come just from the Higgs boson. It can so happen that 2 quarks, a quark and an anti-quark, one from each of the protons, decided to interact and independently produce 2 Z bosons, which again decayed into leptons. So this is what you would call a background. It's not stuff that you're looking for. And this is what you would call your signal. This is what you're looking for. And you need to find out a way to distinguish the two of them. One way to look at this would be, let's take the invariant mass of the 4 leptons. So when you add up the mass of these 2 leptons, it should give you the mass of the Z boson. You do the same thing on this side. And the total mass of these 2 leptons, since they are coming from a Higgs boson, should add up to the mass of the Higgs. So what you can do is take all events in which there are 4 leptons in the final state and start adding up their masses. If the Higgs boson was produced, then you would see a sharp peak in that area. And this is what we're going to try and do right now. So my simulation over here is not working. Excuse me for a minute. I will bring this picture up again, and let me stop sharing for a minute. Okay. Okay, I hope this is visible again. Sorry about this technical issue. So now let's go back to what we were talking about. We are searching for a Higgs boson which decays into 4 electrons. So the mass of the 4 electrons should add up to the Higgs boson. But this is not always the case. The mass of the 4 leptons can add up to any other process. It can add up to this weird Z boson that is produced. It can add up to nothing at all that corresponds to a particle. And amidst all of this, you need to find the Higgs peak. So the idea is to start collecting data. The black points over here are the data points, and assume that there is no Higgs boson. You would try to guess what are the other particles that can possibly contribute to having a peak, possibly contribute to explaining the data over here. So let me stop this here. For example, you would guess that this process exists. So I will try to simulate it. Basically, a Monte Carlo generator is what you would use. And then I would try to guess, okay, this process also exists. So I will try to pick that. I will try to generate it and try to fill up this gap between the data. So basically, I will try to explain the data with what I think it might be. And this is basically called Monte Carlo. Now let's pause again. Right now, at this point where the GIF has stopped, you have all your data in black. You have all the background that you think can explain the data in red and in this other color, purple. But what you see around here, somewhere between 100 to 150, is a small excess. The processes that you considered have not been able to explain why, what this data tells you. So what you do is try to make a hypothesis that, okay, suppose there exists a Higgs boson of mass 125 GeV. Let me see what it looks like, whether it would be able to explain this data or not. So I superimpose this Monte Carlo signal again over here. And hey, it's a good agreement with the data. So it's not as easy as I described it. This is not how it's done. There is a very rigid statistical process where which helps you decide whether, yes, that particle was actually there or not, and a very long, stringent checks that are done to make sure that you're not claiming a discovery just like that you're very, very, very sure. And hey, you found the Higgs peak. Okay, let's move on. Now the standard model, yeah?
I had a question. In the previous graph, is this integral calculating the action LDT? I think is that
sorry.
In this the simulation, there's an integral sign LTT. Like, what is that signifying? Like, what is it showing?
This integral over here is basically a measure of how much data you have. It is called the integrated luminosity. L over here stands for luminosity, and over time you're integrating it. It is a measure of how much data that you totally have. So as time goes on, the amount of data that you have increases. So that is why as you start binning up the data, these data points start to rise. This is a histogram in which is slowly growing. Simultaneously, you produce your, you try to explain it with known processes like the production of, say, these processes, and that is why the red is also growing together.
So I had a doubt that when you're seeing the peak, we try to match the hypothesis. Isn't that we are introducing already a bias in our statistics? Like when we are seeing the peak and we are trying to hypothesize using that peak. Like,
no, that's not how it is done. So this was a very simplified model that I mentioned that, hey, okay, if I superimpose the Higgs peak over there and I see that, hey, it matches my data. But you start off with your null hypothesis, your alternative hypothesis, null hypothesis that no, there is no Higgs signal actually that's there. And you follow the exact rigid process. You finally perform like a fit to the data to actually see whether it's there or not. This was a very simplified representation. Does that make sense?
yeah, kind of, yeah, I think.
Okay.
Excuse me.
Yeah, my question is, we are going to find out the energy, that is the blue one, which you have showing that is nothing but energy of the Higgs boson, right?
That is the number, that is like basically the mass of the Higgs boson. So the events which are going to be showing up in blue are the ones that are coming from this process over here. So it's not the energy of the Higgs boson, but it is the number of events which are coming from this process. And okay, so if there are no more questions, let me move on. So we discussed about the standard model of particle physics today, and we said that it is one of the best theories that we have, one of the most accurate models of what the universe looks like. But hey, there is a problem. There are many problems, in fact. It explains only about 5% of the universe. So the whole of the universe is composed of dark matter, which is around 27%. You have 5% of visible matter that you can actually see and explain. And then you have dark energy. This are the other 68%. And standard model goes for only 5% of this. The next, we do not understand dark energy as well. We are not trying to hit it as far as I know right now. So we try to explain the next thing that we know, that is dark matter. Now, the standard model of particle physics does not have a candidate for dark matter. So there exist many extensions like supersymmetry, one of the things that we talked about, which possibly can have a candidate for dark matter. But the problem is we have not actually been able to find any of these particles yet. We're still looking for them. One of the bigger obvious problems that we had from earlier was that there is no explanation for the gravitational force. The standard model by design explains only 3 of the 4 fundamental forces. Gravity is not included in that. The problem is that we have not been able to quantify gravity. We have not been able to form a quantum or a particle of the field of gravity, which we would theoretically call the graviton. The marriage between quantum physics, so particle physics and astrophysics has always been a very, very sad one. They've never gotten along so well. And any theories that exist which can possibly bind them together are still being tested. We do not have any definite proof for any of them. Now, there exists yet another problem, and this is something which you guys will be exploring in the coming few weeks, as far as I understand. And that comes in with the discovery of neutrino oscillations. Now, the standard model by design assumes that neutrinos are massless particles. This would, in addition, mean that neutrinos cannot change flavor. So if an electron neutrino is produced, it cannot at any point decide to turn into a muon neutrino or a tau neutrino. But results from the Super Kamiokande and the T2K experiments, for example, tell you that this is not really the case. Electron neutrinos can change flavor into muons or tau neutrinos. And the probability term for this to happen, the probability that an electron neutrino will change into, say, a muon neutrino, is actually sinusoidal. And inside the sinusoid sits a small term, a mass difference between the two flavors. So there would be, if you would require to have a mass difference between the electron neutrino and the muon neutrino for the phenomena of neutrino oscillations to actually happen, which means that since there is expected to be a mass difference, they should have a mass. And the standard model does not know how to incorporate this into its theory. Next problem is that of matter-antimatter asymmetry. Why does the universe mostly compose of, why is it mostly composed of matter and not antimatter? What happened to the antimatter? Where did it go? And there are many more mysteries. So it is a very exciting time right now because we have so many things that the standard model cannot explain. We have a huge load of theories that can provide possible explanations for all of this. Sitting here at CERN, we have multiple working groups that we try to, as experimental particle physicists, search for particles that may come from these theories. It's a very exciting time and there's so much to do. And one more question that we usually have is where do you begin? So particle physics is a very, very broad field, and you can go into neutrino physics, you can study the quark-gluon plasma, you can try to search for new particles. My thesis, in fact, is searching for a second kind of Higgs boson. This Higgs boson is, again, supposed to explain some of the tensions that we have seen with the standard model. So the idea is that there is no perfect starting point, according to me. So it's a vast field. You can just pick one topic and you start exploring it. You'll either like it or you will not like it. One way to start is to take online courses. There is multiple platforms like Coursera, FutureLearn, MIT OpenCourseWare that you can use to learn a little bit more theory about what you want to do. Internships are the option that I love the most. They help you reach beyond your textbooks. You get to meet people in real life. You get to learn techniques on what to do, how to do. You get to ask doubts. You get to explore what you might like and what you might not like in a very real scenario. And then there exists, well, let me specifically mention opportunities at CERN, where you can take up technical studentships, internships, etc. There are summer internships with a technical supervisor that would last, say, about one summer. And they are also funded. There are many such opportunities available in India and other countries as well. And I would strongly encourage you to just go ahead, explore, and have fun. And yeah, the most important thing in all of this is to have fun. And now that you can always ask me questions as well. I guess the organizers can share my email address with you. I would be very happy to try and answer any questions that you have, or where to go and so on. Thank you. I'm sure you have a lot of questions and I will try my best to answer them.
Excuse me, ma'am.
Yeah.
Yeah, ma'am, I have a question about that diagram, which shows that it has 26% of dark matter,
Oh,
and
okay.
that one, and 68% of dark energy. Then how you come to know that that amount is remaining? Means that amount is dedicated for dark energy and dark matter. Is there any experiment conducted as before?
Yes, there are experiments which prove the existence of dark matter. Now, so you can use them to sort of estimate how much dark matter you would expect to be present in the universe. So this is related to looking at the rotational curves of galaxies. You would, yeah, I have to look up again on that. But the thing is that the rotational curves of the galaxies would look very different if all the matter was actually concentrated in the center of the galaxy with less matter in the arms, to the other scenario where you also have something on the arms. So V is equal to R omega. And they will be very different if the mass is distributed, say, just at the center versus where it's a disk-like structure. And no visible light, there is no visible matter that is there that can accommodate, that can be seen to be present in the arms of the galaxy. So you would assign this to be dark matter, something that light cannot show us. And this is one of the indirect evidences for the existence of something that is not matter, something that does not behave according to what the standard model tells us.
Okay. One more question. What is the difference between dark matter and dark energy?
That is a good question. I don't know. To be frank.
Yeah.
Hi, ma'am. I have a question.
Yeah.
I have read many times on the net that for the neutrinos we have mass to change from one flavor to another.
Right.
So I don't understand why is this.
Okay. So neutrinos have, let's see, how do we put this? The weak force, the force that we talked about, let me go back to one of the starting places. Where are we? Yeah, okay. So the weak force actually selects, let's say, left-handed particles. So handedness is another quantum number that is intrinsic to a particle. It is related to the direction of the spin and the particle, the momentum of the particle. So the angle between that would, if they're pointed in the same direction, that would, I think, be called left-handed. Or if they're pointed in opposite directions, that would be called a right-handed system. I'm not very sure which is what, but it can be used in it. It's a convention, basically. Now, the thing is that the weak force selects left-handed particles, and or by selects, I mean has interactions with, and right-handed antiparticles. Now, if the neutrino is massless, then the handedness of the particle would remain the same. Now, what actually happens is that the handedness of the, because if you have, say, the spin and the momentum pointing in opposite directions, and you are an observer looking at it, say if you're able to move faster than the neutrino, the direction of the momentum of the neutrino is going to get reversed if you're able to move faster than the neutrino, right? So the handedness of the neutrino changes. And the handedness of the neutrino changing is, and if neutrino is moving faster than the speed of light, then you cannot possibly move faster than it, which means that the neutrino is actually moving slower than the speed of light, which means it has a mass. And this would contribute to it being able to change its flavor. Electrons, muons, and taus, on the other hand, cannot change flavor. They have a fixed handedness, but these electron, neutrino, muon, neutrino, and taus do not have a fixed handedness. This intrinsic property called handedness. You can read up more on the helicity of a particle. That would help you get a better idea, I think, on what I'm talking about.
So the handedness is the basic property. It's like a basic property. But
Yeah.
How did it establish? How did it get established? So we are the ones that made the rule. No?
Right. So we decided that, okay, if the spin and the momentum is pointing in opposite directions, I would call it, say, right-handed. And if it's pointing in the same direction, I would call it left-handed. And my theory tells me that I cannot flip between the two of them.
I said that.
Mm-hmm.
Okay. Thank you.
No problem. But I would encourage you to go ahead and read up on helicity as well for particles in general.
Yes. Okay.
Hello, ma'am. Am I audible?
Mm-hmm. Yeah.
Yes. So in the beginning, we were speaking about the gas detectors, right?
Mm-hmm.
Like to even study the particles. So coming to that thing, I mean, I was doing this research on the gamma ray detection. So it was proven that the semiconductor detectors are better than gas detectors because they show us better results even if there's less energy provided. So like for gas detectors, it is more when compared to semiconductor detectors. So in semiconductor detectors, which is much more efficient than gas detectors, if we can have some type of like similar procedure even in semiconductor detectors, can we have better results when compared to this gas chamber experiment?
I guess so. Well, the point of this gas chamber experiment initially was to, well, measure particles, look at particle decays, the things that you could actually see. But we have much more advanced techniques now to look at the same thing. So
I actually have another doubt when we were speaking about the dark energy. So I've come across this that the Fermi Gamma Ray Telescope is basically, it was basically sent to study about the supernovae. But after some time of analyzing, when they found out about the two supernovas in the Milky Way galaxy, it was actually focused to work on to detect pulsars and dark energy. So if we don't have the proper idea of what dark energy is, then how can we say that even the Fermi Gamma Ray Telescope has come across the dark energy? Because we don't know what dark energy exactly is. So even if the Fermi Gamma Ray Telescope has come across that, then how will we know that if it is for dark energy? And if we don't know what is dark energy, then how can the NASA people claim that it is currently working on detection of dark energy also?
Okay, so I think the idea here would be that you don't know what dark energy is, but you can have a theory for what dark energy can be. You can have multiple such theories, and I'm sure that there is common ground that you would need to search for, common properties that you would try to search for. And I'm sure that, I mean, I have to look up about this detector. I do not know the principle on which it works, but I would assume that we make an assumption of what dark energy is, and we try to search for, try to go along those lines. It is similar in the case of dark matter, for example. We do not know what dark matter is. We make a theory, say supersymmetry gives you a particle that can be dark matter. And now let me search for this particle. If I find it, hey, I found a candidate for dark matter. If I don't find it, let's move on to the next theory. So you don't know for sure what it is, but you have ideas of what it might be, and that's what you look for.
Actually, one more doubt.
Yeah.
Like if we come across any of the things that might belong to the dark energy part, so based upon the experimentations that you can do on that singular, I mean, let's speak about it as a subject. So if you have found something subject from the dark energy side, so if we can conduct some experiments, can we actually predict about what dark energy exactly can be?
I'm not sure I understand your question. Do you mean that you have experiments to show what dark energy is?
No, like not exactly that, but right now we are studying about the particles, right, to understand what can be explored, like in future, what we can come across. So based on that only, we were able to differentiate, right, about the dark matter and the dark energy. So if we come across something new that might unlock the secrets of dark energy, so how exactly can we do that? Like based upon the particle, like we use particle accelerators to understand different types of like this particles. So is there something we can do, not exactly studying the particles, but like suppose I'll give you just an example. Like based on the engine, you can tell about how a car can run, right? Like the horsepower and all these specific things. So if you can study a certain subject which can be something different than we already know, so can we predict about what dark energy could be, something like that?
That's a very difficult question, frankly. And I don't know. I'm not quite aware of what theories exist with dark energy right now. But that's a very good question, yeah.
Hello,
I have
ma'am.
a doubt.
Hello.
Mm-hmm.
Yeah, ma'am, I have a question related to neon G2 experiment, which was recently conducted in Formula. The experiment suggested that there is a new kind of a particle because there was an anomaly. And was there some kind of a news like that? Was there any new kind of a particle in standard model of particles?
So the G2 anomaly basically tells you it's something that the standard model does not accommodate. And to explain that, there are many other theories, extensions of the standard model. One of them is called, say, the vector-like leptons. So you have leptons, an additional bunch of leptons hanging around. You propose that there is an additional bunch of leptons hanging around, but they behave like bosons. So we are starting searches for such particles. We have theories which would try and explain this anomaly, and then we would design experiments which would try to search for particles which can explain such anomalies. And as far as I'm aware, right now we do not have any particle that can explain that. We are searching for them.
Okay, thank you, ma'am.
I have a doubt. We
Yeah.
always say that electrons have associated electron neutrino and all. That what exactly is that association? How they are associated to and why we put them in the lepton family?
Okay, so this association is related to something called the flavor quantum number. And that is again something that is expected to be conserved. Let me not say it is conserved. because right now we have tensions which prove maybe point towards the fact that it's not. But basically, the idea is that electron and the electron neutrino would be produced together in an interaction which is mediated by the weak force. So the kind of neutrino that is produced with the electron would be called the electron neutrino. What they have in common is the flavor, which is electron. Electron is the flavor. In the case of these guys, muon is the flavor, and in case of tau, the flavor is called tau.
Oh.
So the flavor quantum number is what? Yeah.
Hi, ma'am.
Hi.
What kind of softwares or coding skills one need to pursue particle physics, or particularly neutrino physics?
Okay. I would suggest to have a basic understanding of either Python or of C++. The idea is to understand the logic behind how coding works, because that is what you would use to do your statistical analysis or to, well, make your machines work. It does not really matter as much which one you learn, because there's no way to be fully prepared for what you would need in the collaboration. Usually once you get in, they teach you the skills that are necessary. But it's a good idea to have an idea of the logic that goes behind coding. And for that, frankly, any of the languages is a good idea. C++ or C is much higher level, gives you more insight into how to write better code, or how to, in general, gives you much better, is more complicated, and that would probably be a better idea, I would say. But Python is also a good way to go. Yeah.
I have heard root language is used.
Okay, so root is a C-based, I think it is C-based or C++, I'm not sure, a based analysis package. So it is based on C or C++, and if you know these, you can pick up root again. It is built on top of it. It's not a language in itself.
Any particular softwares?
Any particular softwares for data analysis? Root is, well, very commonly used in the particle physics community. One more software that we use is Rivet, but not as widely for data analysis as far as I understand. Yeah, root is, well, the bare basics that you can use. But after that, it really depends on the analysis group that you work with. With different analysis groups, you have different packages which are built on top of root. So root's interface is frankly not the best, I would say. You have other packages like histfitter or T-Rex fitter, which are higher level than root. So, but the choice of that depends on the analysis group that you're working with. I would say start with root, yes. Okay. C++ and then root, maybe.
Ma'am, I have one question regarding Higgs field. So you told that Higgs boson is like the quanta of Higgs field, and moreover you told that Higgs boson can decay to other particles. So isn't somewhat like opposite to each other? Higgs field should give mass to particles. That means how can that itself decay?
So it's not the Higgs field that decays. That's a very good question. It's not the Higgs field that decays. The Higgs field interacts with the other particles to give them mass. Now, how do I know that the Higgs field exists? I excite it. So this excited state is going to be a small packet of energy, you would say, called the Higgs boson. Now, this Higgs boson is what's going to decay. It's not interactions with the Higgs boson that gives a particle mass. It is interactions with the Higgs field, which is, well, present all over space.
Okay, so since the Higgs boson itself has mass, so the Higgs boson reacts to the Higgs field itself. The interaction with the Higgs field.
Yes, that is called the Higgs self-interaction, and the Higgs boson interacts with itself. Yes.
Hello, ma'am.
Hello.
In this this distribution of like the dark matter and dark energy, how are we like on what basis is that distribution?
Well, you can estimate, say the example that I gave of the velocity curve for galaxies, you can estimate the total amount of matter that is there in the galaxy.
No,
Yeah.
what I meant was like, what are we calculating, like the mass or the volume, or like what is the basis of this distribution?
I see. I think, I don't know. I think
like,
this would be the total. Is this mass based? I don't know. I have to check.
Like, should we start looking at something where both are equal, like matter and dark matter and matter are equal? Like, there will be something, right, where those things are equal, may not be mass or something. Like, for example, if we consider a proton and electron, they have different masses, but their charge is same, right? So like that, there might be something where the distribution is equal.
So say you have, let's go back to our old story of the neutralino, the particle that one of the supersymmetry theories tells you. One thing that would be common between that particle and, say, neutrinos is that both of them can interact via the weak force. So essentially that neutralino in some theories would decay to give you neutrinos. So that is some common ground that you would have between known matter and dark matter. But again, you don't know that neutralino is per se dark matter. It is one of the candidates for dark matter. Does that work?
Yes, ma'am. Thank you, ma'am. And another question regarding that we are not able to explain the gravitation in the standard model. What information are we looking for so that we can explain it? Like what things, like that, yeah.
So within certain extensions, I would say, of the standard model, they have proposed a particle called a graviton. As far as I understand, we don't know the mass that we expect the graviton to be at, but there is certain spin that I don't remember, different from that of the standard model particles. It's spin 2, I think. It is proposed to be. And the idea would be to say, look for this quantum of gravity called the graviton. And so far, we have not found it.
Yes, ma'am. Thank you. Thank you.
Yeah, I had a doubt actually. Suppose when we are talking about neutrino oscillation, so as I understood is that each flavor can be written as a superposition of some mass eigenstates, some basic mass eigenstates. So, so what I understood is that if we can write it, we can construct a unitary matrix known as PMNS matrix.
Right.
So for that, the individual element in that matrix, is there a theoretical framework to determine that? Or do we solely rely on the experimentation to determine each and every element in that matrix?
Those are determined via experimentation, as far as I understand.
So there's no particular theoretical framework for neutrino oscillation to exactly predict those elements.
There are no numbers. You have these variables sitting there, but you need to measure what quantity these variables would take. So these numbers are measured from experiment for the PMNS matrix.
So one thing I've understood that if a neutrino starts an electron neutrino, at its end journey, it will also be an electron neutrino. Like, is there any way, like in the middle, we can accurately measure the probabilities of how much it is like oscillating between back and forth? Is there any standard method to exactly?
Yes, there is. So it is not the case that an electron, when you started looking at an electron at the start of its journey, and when you look at it once it has ended its journey, that it would still be an electron neutrino. It really depends on the energy and the distance that the electron neutrino travels. And yes, there is a probability equation that you can calculate with some very basic quantum mechanics to predict that, given the energy that I start with of the electron neutrino, at what distance I would expect it to turn into a muon neutrino, and at what distance I would expect it to turn back into an electron neutrino. So suppose I want to detect the muon neutrino, I would look at this equation which tells me, say, at 100 kilometers from my source, I would expect the maximum number of electron neutrinos in my beam to have turned into muon neutrinos. So that is where I'll place my detector. So what you could look for, I guess, is, say, a quantum mechanical treatment of neutrino oscillations. That's one thing you can Google. It's few lines based on the mass eigenstates that you were talking about.
So it's like basically it just works like other quantum mechanical treatments that like from state 1 to state 1, there might be some transition between state 1 and state 2, and there is this transition probability V. So it just works on that framework only, right?
Essentially that, yeah.
Ma'am, I have a question. How does the mass of W and Z bosons play a role in their interactions?
The mass of the Z and the W bosons, okay.
Or like any other bosons, like any other force carrying particle.
Well, one way to talk about it would be to go back a little bit to the one topic that I have decided to leave out a little bit, but I would encourage you to look at it. So the electromagnetic force and the weak force can, at some point of the universe, were actually this one and the same force called the electroweak force. So you did not have electromagnetism or the weak force. You had one force with 4 carriers, photon, W plus, W minus, and Z, all of them having the same mass. And then I told you that to give mass, the Higgs field got switched on after the Big Bang. So what the Higgs field did was break the symmetry, break the electroweak force into electromagnetism and the weak force. The carrier of the magnetic force was left massless, the photon. The weak force was given, the 3 bosons from the weak force were given mass. Now, this results in a difference of their interactions because the photon is electromagnetism is a long-range force. The strength of the interaction would die as the r square and over 1 over r square. But for the weak force, it is not a long-range force because of the very fact that it has the carriers of the weak force have mass. So that is one role that the mass would play in distinguishing interactions.
Thank you, ma'am.
Ma'am, I have a question. So just like we're looking for new particles, are we also trying to look for new properties, like other properties of particles that we don't know of?
Let's see. Yes. While we also look for new particles, we also try to look at the known particles and verify that if what we see in the experiment is in line with what we expect from theory. One of the examples is the interactions between the top quark, the guy sitting over here, and the Higgs boson. So let's go back to this mass. Their masses they're super heavy. And there is a problem with the way the top quark actually gets mass from the Higgs boson. And because of this problem, you would expect the Higgs boson to be super, super heavy. But what actually happened is that you saw Higgs at, approximately the same mass. Now, the thing is that this was, again, an unexpected. And yes, so now the fact that you're studying the properties of the top quark or the Higgs boson is going to help you understand if your standard model is actually good enough to explain how these guys behave, or if you need anything new. So there are parallel efforts to find new particles and also verify that whatever we know about the standard model is verified experimentally or not. The theory and experiment match or not.
Okay, so the reason why I asked this was, like, in a previous example, we saw how we could identify a neutron, right? Like, it passes through the tracker and it hits HLAC, like it doesn't like hit the tracker. So there could be another particle that behaves the same way, but just because we don't know of another property which could be distinguishing that particle and the neutron, we might have misidentified the neutron. So could that also be a possibility?
Yes, that is in fact a possibility. So what we assume with this detector is that all the particles, new heavy exotic particles that are produced at the collision center or around the collision center, decay into electrons and other standard particles before they hit the detector. So you can reconstruct them back. But recently efforts have started in our at CERN where there are new particles called long-lived particles. So say a long-lived neutral particle would be somebody who passes right through the tracker, does not leave any information there, does not leave any information on the ecal, but once it reaches the hcal, it starts to decay and leaves a bunch of activity in the hcal. So there is a small chance that this could be misidentified as a neutron, but it was indeed a heavy particle. But then what you can do is go back to simulations and look at other particles that look at other properties of this particle. For example, so when a particle interacts with the calorimeter, it sets off something called a shower of electrons and photons, just like lightning in the sky, for example. And these showers from a neutron and say some other particle would look very different. You can simulate these things. You would expect them to be very different. And this is one way that you can try to distinguish the two of them.
Yes, ma'am. Thank you, ma'am.
That's a very good question, because this assumes a lot of things, the standard model and this detection technique.
Okay, I had a small question. Earlier, you mentioned that there are three colors of quarks: red, green, and blue. Are they just arbitrary namings, or is there any specific property related to that color?
So they are arbitrary namings. We try to be not so fancy, I guess. But these are arbitrary namings. The idea at the end of the day is that RBG together form white in a way. So in a way, this would be, you need to form color neutral states or white states. And you could do this by putting R, B, and G together. So that's, I think, one of the origins of why it is called color. One other way you could do this is by taking an R and an anti-R. So basically a quark and an anti-quark together, and they together is again going to form a stable bound state because the total color is 0. But yeah, it's arbitrary.
Okay, thank you.
Yeah.
Hello?
Hello.
Yeah. Sagar, continue. I just wanted to say we can take about 2 more questions. It's getting fairly late, so I don't want to keep her for too long. Yeah.
Okay. So my question is regarding supersymmetry. Is there a way how we can show supersymmetric particles and normal particles interact? Or what forces would they mediate?
So in these some of the supersymmetric models, what happens is you have the standard model over here. You double the total particle content of the standard model. So for every fermion, you have a partner boson. So if you have, say, an electron in a supersymmetric model, in addition to an electron, you will have a selectron, a supersymmetric electron. Not very creative again over there. So you would have additional forces that are produced. So because this electron from the standard model is a fermion, so it makes up matter, but this electron from the supersymmetric extension is actually a boson. So that would result in, it's going to be a new kind of force carrier altogether. You would expect it to, well, say have weak interactions as similar to as the electron. So you would expect it to decay to an electron at some point and some other particle. So interactions, again, I mean, it really depends on how, what kind of extensions you decide to make to your standard model. And that would depend on what you're trying to explain, what anomaly you're trying to explain.
Thank you. And if bosons have super partners as bosinos, that would be a fermion that could contribute for dark matter candidates, no ma'am?
So in the supersymmetric extension, you do not have, so each boson does not really have a one-on-one partner. There are more bosons that are also produced, and this actually happens because the topic that we talked about earlier, electroweak symmetry breaking, when the Higgs field gets switched on in the standard model and breaks the electroweak force into electromagnetism and weak, something similar happens in supersymmetry as well. But in this case, you have many more particles. So you have many more final states that are produced. One of them is called the neutralino, which does not have a counterpart in the standard model. But yes, that is one candidate that people have proposed as a dark matter candidate.
Thank you very much. Thank you.
No problem.
Okay, so one last question. Yeah, go ahead.
Ma'am, I have another question. So, in nature, can only colorless particles exist stably? Because everywhere I read, we see that even the hadrons and neutrinos, the quarks make them up. I mean, not neutrinos, like just the hadrons. The quarks make them up in such a way that all the colors combine to form white. And yeah, so is it a necessity that particles should be colorless to exist?
Yep. So according to the standard model, it is a necessity, but there are extensions again in which you have colored hadrons that can exist. So these colored hadrons will have very different interactions with your detector. Those there are searches for colored particles that are actually also ongoing with both the Atlas and the CMS collaborations. So far, we haven't found anything yet, but yes, that's a possibility. So really what the standard model is a bunch of assumptions that work, that you have been able to find experimental proof for. And now all of a sudden you see that the standard model is not enough. So you try to make clever guesses on how you could modify it or find an entirely new theory on to explain the crazy stuff that you're seeing in your experiments.
Okay, I think we will stop the questions here. If you would like to take a minute, Shalini, to just summarize your experience at working for Atlas so far, that would be a wonderful end to the session.
Okay. I love it. It is a dream come true. I have always wanted to be working in particle physics. I find it very exciting. And this is really fulfilling that my institute decided, it's in Spain, and my supervisor is in Spain as well. And it's very, I don't know, I'm super grateful that they decided to put their PhD students at CERN. It is an amazing experience because there is always so much to do and so much to learn. Not everybody knows everything. So what matters is that you find the right person to ask questions. You will always have questions and you will always have people who will explain things to you. And basically waking up every day, you start to look for new answers. You push yourself as much as you can, and in the process also have fun. So personally, I love it. Everybody over here is super helpful. And well, it's like a little family, I would say, working with these guys.
Thank you. I'm sure that will inspire a lot of people to get a little bit more excited about particle physics. So that was extremely informative. Thank you so much for your time.
Most welcome. And if I may add, Sitara, I will pass my email address to you. And if any of them have any questions that they would like to ask, you could just write an email to me. Could you please share it with them later?
Yeah, so Sagar here is kind of like the leader for this group, which is working on the particle side of things. And there are about 40 people in that particular team. So what we'll do is we'll also collect questions on a weekly basis because they're going to be extremely active over the next 4-week period. And also from your side, if you're up for a personal discussion with just about 8 to 9 of us, just let us know when that would be ideal for you. So maybe not next Sunday onwards, it will be a smaller group of people and we'll just have some private conversations with you.
Okay, sure.
Yeah.
That'll be good.
That will be quicker and we'll directly get into the biggest doubts we've encountered so far and so on. So we'll work from there.
Sure.
Okay.
That sounds really good.
Thank you so much. Sagar, if you have any final thing to address in terms of what you want to do this week, you can take a minute.
Right now, I don't have anything, Sitara, but in meeting with Shalini ma'am, I think I'll have so many doubts to ask.
Okay, then great. I think they're focusing on oscillations this week, right? Yes, you're going
This is regarding basics of particle physics only, because a strong foundation of particle physics is required for other factors, right? Coming weeks.
Okay, cool. So then you can summarize whatever you learned this week and we'll have the meeting next Sunday. Okay, thank you so much. We'll see you again, Shalini. Thank you so much.
Thank you so much for having me.
Wonderful. Yeah. Thanks, everyone. See you guys
Bye
tomorrow.
and good night.
Bye.
Hey, I'll end the meeting then.